Hello guys, in this video we are going to be looking at concentrations of solution and its units. Here I'm going to be walking you through the introduction to solution and concentrations of solution. We're also going to look at useful conversion factors that we often use in this topic. Also, we are going to consider the chemical and the percentage unit of solutions. So let's get started. What is a solution? Or let me say, what are solutions? Solutions are usually composed of two parts. As we all know, we have the solute and the solvent. The solute is a substance that is dissolved by the solvent. The solute is always in small quantity. As a result of that, we often call it the minor component of the solution. While the solvent is always in large quantity. Due to this, we call it major component of the solution. Because of its own larger portion present in the solution, its state determines the state of the solution. What does this mean? It simply means that if the solvent is in solid state, the solution will also be in solid state. If the solvent is in liquid state, the solution will also be in liquid state. And if the solvent is in gaseous state, the solution will also be in gaseous state, because of the fact that it is the major component of the solution. So its state helps us to determine the state of the solution. The solute is the minor component. So regardless of the state, it is not the determining factor for the state of the solution because it is the minor component. We used to have a wrong mindset that the solute is always in solid state. This is wrong. The solute can be in solid state, gaseous state, as well as liquid state. Because we can have solute in liquid state, as in alcohol, then the solvent, which is the major component, is water. When we mix both of them together, they become solution. In that case, the solute is in liquid state, the solvent is also in liquid state. They will form a solution like beer. Another example is gas. The solute can be in gaseous state, while the solvent is in liquid state. They will form solution in terms of carbonated drinks. So the solute can be in any of the state of matter, as well as the solvent too can be in any state. But the state of the solvent helps us to determine the state of the solution, simply because it is in larger percentage. So solution simply means when a solute is dissolved in a solvent. There are two types of solution. We have the homogeneous and we have the heterogeneous. Homo and hetero. In homogeneous solution, as you can see here, in homogeneous solution, there is complete interaction between the particles of the solute and the molecules of the solvent. That means the solute and the solvent, they interact very well. As a result of that, it is always involving a single phase. For example, dissolving salt in water, which will form salt solution. In case of heterogeneous solution, it does not involve complete interaction between the particles of the solute and the molecules of the solvent. As a result of this, we can have more than one phase. We can have two phases involved, three phases involved. For example, shawarma. Shawarma is composed or is formed from different substances, of which we can see all the substances that form shawarma. Another example is pizza. We can see the components of the solution. Vegetable soup is another example of heterogeneous solution. So heterogeneous solution does not involve complete interaction between the solute and the solvent. Due to that reason, we can say that it always involves more than one phase. While in homogeneous solution, a single phase is involved. Now, we have been talking about solution. What do we mean by concentration of solution? Since we have already known that solution is formed mathematically by saying solute plus solvent will give us solution. What's now the difference between concentration of solution and simply solution? Concentration of solution is defined as the amount of solute, which can either be in grams or mole, that is dissolved in a specific volume of solvent, either in liter or Dmq. So that is the definition of concentration of solution. This basic difference is that in concentration of solution, we are able to weigh the amount of solute by using a chemical balance. We weigh the solute, then we dissolve it in a specific volume of solvent using a graduated cylinder in the lab. Because we're able to collect the data involved in the solution, it will be easier for us to calculate how conc the solution would be. And that's what simply separates it or distinguish it from solution. Now that we have examined the basic difference between solution and concentration of solution, and we have looked at the components of the solution and the types of solutions. Now let's go to the useful conversion factors that we have in this topic. In this topic, there are some conversion factors that are very useful when dealing with problems related to this topic. The first one that we must be familiar with is 1000 centimeter cube is equals to 1 Dmq. Because of the fact that in the lab, the cylinders are graduated, which is known as volumetric flasks. They are graduated in centimeter cube. That means they are calibrated in centimeter cube. As a result of this, we may want to convert it from centimeter cube to Dmq. That is the volume. To convert it, we'll be needing a conversion factor of 1000 centimeter cube equals to 1 Dmq. Another useful factor is 1 Dmq is equal to 1 liter. That means I can say that 12 liter is the same thing as 12 Dmq. We have to take note of that. Another conversion factor is 1000 gram is equals to 1 kilogram, which is useful for the chemical units we are going to look in the next section of this video. 1000 gram is equal to 1 kilogram. Now, let's consider another conversion factor, which is 1 milliliter is equal to 1 centimeter cube. These are the useful conversion factors that we have in concentrations of solution. Now that we have looked at them, let's move to the next section, which is concentrations expressed in chemical units. So, the first one we are going to consider is known as molar concentration, which is also known as molarity. What does it mean? It is defined as the amount of solute in moles dissolved in 1.0 Dmq on 1 liter of solution. Mathematically, molar conc, as we have defined, we say it is the amount of solute expressed in mole dissolved in 1 Dm cube, which is, let me write it as volume of solution expressed in Dm cube or liter. As a result of this, we can simply write it by saying C to represent molar conc. Amount of solute is in mole, which is N, and volume of solution should be V, equation 2. From here, we can get the units for molar conc. As you can see, molar conc, we said it is the amount of solute that we have in mole over volume of solution in Dmq. That means it is going to be mole per Dmq as its unit, or we say mole per liter. That means whenever we see a solution having mole per Dmq, it is simply representing the molar concentration, which is also called molarity. Most times, we will not be given the volume in Dmq. Like I've said, most of the measuring cylinders in the lab, graduated cylinders, they are expressed in centimeter cube. So whenever we are given the volume of distilled water, for example, to be 500 centimeter cube, we need to convert it from centimeter cube to Dmq by divided by 1000. That's why we have analyzed the conversion factors that are useful in this topic. Sometimes we don't usually write it as mole per Dmq or mole per liter. We simply write it by saying molar. That is, one capital letter N is known as 1 mole per Dmq. They are the same thing. For example, I can say 0.5 mole per Dmq is also written as 0.5 molar, capital letter N. 0.02 molar HCl can also be written as 0.02 mole per Dmq HCl. So we have analyzed the first chemical unit that we have for concentration of solution. Now let's look at another important unit, which is known as molar conc, otherwise called molality. What is molality? Molality is the amount of solute in moles dissolved in 1 kilogram of solvent in the solution. As we have said, let's look at the formula. Mathematically speaking, molar conc, which is also called molality, is amount of solute still expressed in mole over weight. Since we are saying 1 kilogram, weight or mass of solvent in kilogram. So from here we can get the unit for molar conc. The unit for molar conc is going to be, since amount of solute is expressed in mole over weight of solvent is in kilogram. So that means the unit for molar conc is mole per kilogram. That means anywhere we see mole per kilogram, it simply represents molar conc. But if we see mole per Dmq, it represents molar conc, which is known as molarity. Please, let's try to take note of the difference between the two. They are similar in terms of pronunciation and volume and weight of solvent and solution. So most times they will not give us the weight of solute in kilogram, simply because 1 kilogram is a large value. So they will give us, or they will express the weight of solute in grams. We are given the weight of solute, for example water, to be, let's say, 200 kilograms. That means we need to convert from gram to kilogram. That means to divide by 1000 should give us 0.2 kilogram. You can feel free to pause the video so as to check the conversion factor from gram to kilogram. Now let's move to the third one, which is known as mass conc. Mass conc, which is another concentration of solution units, can be defined as the amount of solute in grams dissolved in 1 Dm³ or 1 liter of solution. Mathematically speaking, we say it is the amount of solute. Now it is no longer expressed in mole, it is expressed in grams, dissolved in 1 Dm³ of solution. That's volume of solution is in Dm³. And we have said 1 Dm³ is same thing as 1 liter, also be expressed like this. Question 2 first, 3 rather. Why this represent question 4? So here, mass conc, amount of solute in gram over volume of solution in Dm³ or liter. We can also obtain the unit for it as the amount of solute is in gram, volume of solution is in liter. So mass conc is expressed as gram per liter, or we can say gram per Dm³. That means anywhere we see the concentration of solution to be expressed in gram per liter or gram per Dm³, it is known as mass conc. Now you will notice that mass conc is quite similar to molar conc. Yes, they are very similar, but they don't mean the same thing. Mass conc works with the amount of solute to be in gram while molar conc works the amount of solute to be in mole. As a result of their similarities, we have an expression to show or relate the two together, and that it is given as, let's write this as molar conc, which is in mole per Dmq, is equal to mass conc, mass concentration as we all know, over molar mass. So what relates the two parameters that we have, which are molar conc and mass conc together, is simply the molar mass. So that means if I'm able to get the mass conc, I can use that to get molar conc. If I've gotten molar conc, I can use that to get the mass conc as well. So we have looked at the three major units that we have for solutions. Now let's move to another one, which is known as normality. The fourth one, normality. Normality is defined as the number of equivalents of the solution contained in 1 liter of solution. In another way, we can say that normality of a solution is defined as the number of replaceable hydrogen ions from an acid or hydroxy ion from an alkali multiplied by molar concentration of the solution. Mathematically speaking, normality is defined as the number of replaceable hydrogen ion from an acid or replaceable hydroxy ion from a base multiplied by the molar concentration, which I can simply write as N is equals to small letter n multiplied by concentration symbol, molar concentration, precisely, question 6. That means if you ask to solve for the normality of a solution, you only need to know the concentration of the solution and the number of replaceable hydrogen ions. Take for example, let's say 0.02 molar H2SO4 that we have. I've told us that molar, this which is capital letter N, can also be expressed as mole per Dmq. That means I can simply write it as 0.02 mole per Dmq of H2SO4. Here, the molar concentration is 0.02. Now, how are we going to get the normality? We only need to know the number of replaceable hydrogen ions. Since we are dealing with an acid here, we have 2 replaceable hydrogen ions. Since if we try to dissociate it, we are still going to be looking at that. In our subsequent videos, we will consider chemical equilibrium and ionization. Here, if I am to dissociate H2SO4 in aqueous solution, it's going to give us 2H plus SO4 2 minus in aqueous as well. That means the number of replaceable hydrogen ion is 2. Therefore, to solve for normality, we are going to be having N is 2 times concentration, which is our molar concentration, is 0.02. Then our answer becomes 0.04, which is in mole per Dmq as well. Here, we have been able to calculate the normality of 0.02 molar of H2SO4. That is how we calculate normality. Now let's look at the last chemical unit, which is known as mole fraction. Number 5, rather. Yes, we should be in number 5. Yeah. Mole fraction is defined as the number of moles of any component divided by the total number of moles of all the components in the solution. Mathematically speaking, x represents mole fraction. So whenever we see x, it simply means mole fraction. I represents the particular component I'm talking about. So in that case, xi, that's mole fraction of component I, is defined as the number of mole of component I over the total number of moles of all the components that we have in the solution. Question 6. What is this trying to say? For example, we have two substances that form the solution, A and B. The mole of A, let's say it is 0.2 in mole, and the mole of B is 0.1 in mole. If we want to get the mole fraction of A, which is expressed as XA, that is going to be number of mole of A over total number of mole. If I want to get the mole fraction of B, it's going to be number of mole of B over total number of mole. And how do we get the total number of mole? But since we already said that A and B, they are present in the container, both of them form the solution, that means the total number of mole is going to be number of mole of the first component plus number of mole of the second component, and we can solve for it that way. We should also take note that the mole fraction of all the components is always equal to 1. What does this mean? That means if I'm using this A and B, for example now, the mole fraction of A plus mole fraction of B will always give us 1. That we can have a mathematical expression for it by saying summation xi will always be equal to 1. That means if we have 3 components inside the containing vessel, component 1, 2, 3, this assumption still holds that mole fraction of the first component plus mole fraction of the second component plus mole fraction of the third component will give us what? 1. If we solve for the mole fraction and it's not equal to 1, that means something is wrong with the solution and you have to check from the start, or you go back to the scratch. Now, we have considered the concentrations that are expressed in chemical units. Let's also look at concentrations that are expressed in percentage. So, the first one we are to consider is percentage concentration weight per weight. Conc weight per weight. What does it say? It says that it is the weight of solute in grams present or dissolved in 100 grams of solution. Let's analyze it. Since we are dealing with percentage weight per weight, and we know that two components of solutions are solute and solvent. They both form solution. That means percentage concentration weight per weight means weight of solute with respect to weight of solvent. And since it is percentage, it is always expressed with respect to 100. Weight is expressed in gram. So if you are to define it, we say it is the weight of solute, the weight of solute or mass of solute, which is in gram, over weight of solution in gram, because we define it as the weight of solute in grams present or dissolved in 100 grams of solution. Why are we using 100? Because of the fact that we are concerned about percentage. So it is weight to weight. Now, let's take for example, if we write 25% weight per weight, let's say H2SO4. There are two ways we can interpret this. The first one is to use it with respect to the solvent. The second one is to use it with respect to the solution. So let's say we are using it with respect to the solvent, and I want to interpret 25% weight per weight of H2SO4. I'll simply say that 25 gram, since I'm dealing with weight to weight, 25 gram of H2SO4 is dissolved, or let me say present, in with respect to the solvent. That means since we are dealing with 100, that is 100 minus 25, which will give us 75. That means 25 gram of H2SO4 is present in 75 gram of the solvent. I can also interpret it with respect to the solution by saying 25 gram of H2SO4 is present in 100 gram of the solution. Since the whole solution is expressed in percentage, so it's going to be 100. So whenever we are giving weight per weight, it is always the solute with respect to the solvent or the solution. Now let's look at the second percentage unit, which is percentage concentration volume per volume. Volume per volume. As we have said the other time, that we are interested in two components of the solution, which are solute and solvent. So the first one is for the solute, while the second one is for the solvent. So if you are to explain this, or to define it rather, we say this is the volume of solute. Now it is no longer going to be in gram, because weight goes with gram. That means since we are dealing with volume, we are going to be using with respect to centimeter cube. So we will define percentage concentration volume per volume as the volume of solute in centimeter cube dissolved in 100 centimeter cube of the solution. Why is it like that? As we have said, percentage volume per volume. That means the volume of the solute is centimeter cube with respect to the volume of the solvent in centimeter cube, or the volume of the solution in centimeter cube as well. So as we have said, percentage concentration volume per volume is going to be volume of solute in centimeter cube, which is dissolved or present in volume of solvent. But since we are using with respect to solution, we say which is dissolved in 100 centimeter cube of the solution. Why are we using 100? Simply because we are dealing with percentage. This unit is common in hard drinks, alcoholic drinks, liquor. For example, you check McDowell or you check some expensive drinks, you will see they will label it as, for example, you see something like 43% alcohol. I've seen something like this in some drinks. You see some they write 12% alcohol. So what does this mean? How do you interpret as a chemist? For example, let's start with the first one that says 43% volume per volume, let's say alcohol, which is ethanol. Let's say, for example, ethanol, ETOH. Now, if you have to interpret this, I can interpret using solvents. We can also do so using solution. With respect to solvents, that means 43 centimeter cube, since it is volume to volume, 43 centimeter cube of alcohol is dissolved in 57 centimeter cube of water, which is distilled water. I've used it with respect to the solvents involved. We can also interpret with respect to the solution, which we can simply say that 43 centimeter cube of alcohol is present in 100 centimeter cube of the solution. So that is another percentage unit. Let's look at the last percentage unit, which is known as percentage concentration weight per volume. Percentage concentration weight per volume. You can feel free to try and define this. As we have said, the first one is meant for the solute, while the second one is meant for the solvent. The solute, since the solute is expressed in gram, in weight, since the solute is weight, we are dealing with the weight of the solute. That means we are going to be expressing it in grams. And for the solvent, we are dealing with volume, so it's going to be expressed in centimeter cube. So if you are to define percentage concentration weight per volume, we say that it is the weight of solute in grams dissolved in 100 centimeter cube of the solution, or we say dissolved in a particular value, a particular volume of what? Of the solvent. Now we can say that percentage weight per volume is going to be weight of solute, which is expressed in gram, as we have said, over volume of solution, which is expressed in centimeter cube. Sorry, I forgot to include 100. Since we are doing percentage, please let's try to include 100 in our equation. We are doing percentage, so let me add 100 to all of them, to the percentage unit. Okay, so for that, so we have looked at the third one. So here in this video, we are only considering the unit for solution. You can check my channel to look out for problems that are related to this topic. I'm going to be uploading a video that has all the problems related to this topic. Thank you.